make sense to say the expansion of space has stretched out our light's wavelength, but this is a bit deceiving. Alright, so the relativistic Doppler effect. Even though light is a quantum object and we could describe it as a singular particle, you can only explain the Doppler effect when we visualize light as a wave. You can explain it using Newtonian physics, which I will right at the end, but it's not physically accurate. As a wave impinges or collides with a surface, the crests impact a certain amount of times over a specific time period. We use seconds as the time period and thus hertz as the frequency. The inverse of frequency, therefore, is how long it takes for a single crest to arrive after another. This is called the period. When the object or wall in which our wave is colliding with is moving away from the direction of propagation, then the distance, and therefore time, each subsequent crest needs to travel before colliding with our wall, increases. If motionless, our wavelength is simply the speed of the wave times the period. However, now our wavelength is the speed of the wave times our new period, and our new wavelength is the old wavelength plus the recession speed of the wall times the new period. We have one unknown, so we can solve this equation. We just rearrange it first to isolate the new period, and in doing so we can clean it up a bit and introduce a new variable beta. Now when we isolate t, we can move c to the left side. Lambda over c is the inverse of frequency. We can now calculate the new period. Or, better yet, the inverse of the period is the frequency. Our new redshifted frequency is the original frequency minus the same frequency times beta, or the ratio between the two speeds. Now that we see it requires a little extra time for our wave crests to impinge after another, it's important to ask, relative to who? As our objects begin receding from each other at relativistic speeds like we see from spatial expansion over billions of light years, time slows down relative to one another. So we need to apply a Lorentz transformation to our new frequency. And this is actually really simple. A Lorentz transformation tells us how the perceived dilation of time or contraction of space appears on a fast-moving reference frame compared to someone outside of it. So if we look at the new frequency from our previous Doppler formula, this new frequency is what we would expect to see if time passed the same as it does at the source of light. However, it doesn't, so we just apply a Lorentz transformation. Now we can predict our new frequency at relativistic speeds. When redshift is described as space stretching the wavelength, it's done so because it's simply easier, and technically not wrong. But what's actually happening is that during the light's journey from wherever it was emitted, Earth's frame of reference continues to expand or accelerate away from the light's current position in space. This rate of acceleration decays as the light gets closer, but when light takes multiple billions of years to reach Earth, it has a long time to keep accelerating from the source's reference frame. Lastly, what about a singular photon? Light can indeed be described as a particle, so redshift should make sense on a particle sense. And it does, but also due to the nature of light, doesn't. Even though light doesn't have mass, it has momentum. So we can simply picture a Newtonian example. If a particle collides with a wall, its strength of impact can be strengthened or weakened by moving the wall towards or away from the particle. A Newtonian particle gets its momentum because each particle has its own unique frame of reference, whereas a light's momentum is dependent on the frame of reference which measures it. Not to mention, to whoever observes the light on impact, it appears to be traveling at the correct speed of light. So it's not a great way to visualize it, but conceptually yes, the acceleration away from points in space means when a particle of light reaches us, it's lost a lot of its momentum. And that's why we experience a redshift of ancient intergalactic light.